Hello. So we're gonna go through. I'm just gonna do a quick overview of how FPGAs. Well, not how they work, but some basics on how that functionality works and how that works with microchips in general, and then how FPGAs use that information to create um, uh, retro gaming experiences that are very true to the original functionality of the systems. So I did a video just recently, within a couple days. I did a video on my Mister setup. And the Mister device is an FPGA based emulation device that a lot of people have built cores for retro gaming and arcades. Um, they I just and I wanted to follow that up with just a little bit of information on what an FPGA is and why it can be used for that purpose and why it's a little bit different from emulation or um, I'm not going to go too far into the weeds on that. That's a discussion that can sometimes be a little bit controversial on whether FPGA systems are better than emulation or if emulation can be more accurate with today's technology. That's not a question that I want to touch on. That's not the scope of this. I'm just trying to talk about the FPGAs themselves and how they work. Again, I'm not going to go highly technical with this. It's going to be um, pretty layman's level information. So, brief description. Let's go ahead and talk about first, and it might seem like it's off the subject, but it'll come back around. How microchips in general work. So everybody knows what a microchip is. They know that they're basically the brains in all of our technology, and well, almost all of our technology. There are some variants that use other types of logic functionality, but modern day, almost everything is using microchips as controllers. The reason that microchips work for that purpose is they have the ability to do high level, complex logic instructions based upon user input and then convert that to a real world output or return information back to other systems that can interpret it. Now, the reason that I'm going to be talking about it is the way that they do those things are based upon are the very basic building blocks of all of that circuitry and information comes down to logic gates. Um, and that's primarily what we're going to be talking about a lot today. Is these logic gates are basically the ways, the real low level way that instructions can be broken down into. So if I tell a computer to add 5 plus 10, what it's actually doing is it's breaking those down into, and it's an addition function that whenever you break it down, it's adding the binary of a 5 value to a 10 value and then producing an output digitally, using it's a complex but fairly uncomplex compared to other systems logic gate functions. And so I want to go over a little bit about logic gates themselves and what they do. I'm not going to go how they function or why they work. I'm just going to go over basic information about what they do, what they are, and what they do. So I'm going to pull up my little white pad here. And so there are a number of different logic gates. I'm going to talk about the simplest of them. I'm going to talk about 4 of them. There's the AND, the OR, the NAND, and the NOR. They're fairly uncomplex to understand how they work or what they do. Again, I'm not going to go into how they work. I'm going to talk about what they do. The bottom row here, I'm not going to get into, except for maybe I can briefly touch on at least I'll need to talk about the NOT, but I'm not going to talk about any of the other ones right now. So, can you see my cursor? Yeah, it looks like you can. All right. So the AND gate, NAND gates, OR, and NORs are the 4 most basic functionalities. And this is just a quick image that I was able to find to just for these gates. And actually, let me go ahead and I'm just gonna get rid of these so that we don't get confused. Just right now. All right, so first I want to talk about the AND gate. Up here. Rid of the rest of them for now. Okay, so very simple. An AND gate is, and the way that these work is they produce an output based upon what inputs you give them. They can be strung together to make more complicated circuits, but whenever you break it all the way down to the gate itself, it's how it works in a very simple way. Well, not again. It does very simple work. So an AND gate works that if you have input 1 and 2, both high or positive or on or true or however you want to look at it, then you will get a positive output from the output. So it takes 1 and 2 to provide an output. So both of these inputs both have to be live, and it will provide an output, and that's where it gets the name AND. So 1 and 2 equals positive. So true and true equals true. I'm saying it multiple times. I'm just trying to make sure that it's clear that that it whenever it says AND, it requires both inputs to both be active. All right. Oh, hold on a second. I just got. Okay. And so now we'll go through all of them. This. So an AND gate requires positive and a positive to provide a positive output. An OR requires either +1 or +2 to provide a positive output. And that way, if you have either input being positive, then you get a positive output. And my volume and speakers are not set. Give me just a second to set this. And I could have done this all in an edited video and produced it on YouTube, but I actually prefer the live off the cuff conversation, or not conversational, but I don't have enough followers to really have a conversation, but to just the ability to just kind of be more off the cuff with my with my videos. So that's why I am doing it in this format. There are other people that have gone into a lot more detail on a lot of these subjects, more than I'm capable of. But I'm not trying to provide that. I'm just trying to give my little 2 cents on the subject as I understand it. All right. So now I was saying the OR, either one of the inputs can be positive and you'll get an output. Then the prefix in before the NOR and the NAND gates are basically, they do the opposite on the output, and I'll follow that up after the NOT. So what a NOT does is it simply inverts an input. So when it receives a positive, it always produces a negative, and if it receives a negative, it always produces positive. It just swaps whatever the logic function is. So whenever you put the NOT on the output of a NOR or a NAND gate, it just makes it work in the opposite of the original. So a NAND will provide a positive output unless it has a positive output on both 1 and 2. And then the NOR will provide a positive output only when there is neither input on neither 1 nor 2, and that's where they get their names. So that's the basic understanding of an OR, NOR, and a NAND. Whenever you place these things together in chains, along with some of the other types of gates, you get basic functions that can do things like calculations and then build more complex logic. That is what a microchip is. It is a series of gates that are placed. And actually, I'm just going to do a quick search right here. Addition. All right, so new layer. Oh, that's only a partial picture. I'm trying to just get a picture of an adder circuit. All right. So this is an adder circuit. And I'm not going to go in, again, I don't want to go into too much detail on this, because I don't want this video to take forever, and I don't want to go into full understanding. But this is an adder circuit. and this is what is used for basic summing, and whenever you put them in different sequences, you can get other functionalities and things too. Um, but it's basically how you sum an input with a carryover, and that whenever you daisy chain enough of those, you end up with being able to sum in binary two binary values. Again, I don't want to go too far into the weeds on this stuff. I'm just trying to explain. So, whenever you are able to do that, whenever you're able to do these mathematical sums and large, massive numbers of these things all at one time, or in parallel, which would be all at one time, or serially, what after the other, fast enough that you can build complex logic out of, and be able to take that. And well, what microchips do now is amazing. They have so many of these things, and they're arranged so that they can do massive logic output calculations with really in binary, and then being able to convert from what we consider now as pretty uh, plain text programming languages, and compile that down so that the computer can turn that into these functions that through these logic gates it can generate the output that you're looking for. That is very broadly explained how a microchip functions. So, oh, my headphones just decided to power off on me. So give me 1 second. I think I just used the power cord that I was using to power them. Huh. On something else. I don't have one available. I don't think offhand. Let me just check real quick. Nope, nope. I apologize for this. Okay, so we'll see what happens. I'll let it go for now. I'm just not gonna be able to hear how the mix is working if the music comes back. But all right. So very broadly, that is generically how microchips function. Well, an FPGA is, it's basically like well, the name kind of tells you what it is. FPGA stands for Field Programmable Gate Array. So it is literally an array of logic gates that can be it is literally an array of logic gates that can be programmed in a live functionality. So as needed, it can be flashed, or it doesn't require the same functionality as when you flash a microchip or a ROM chip or something. It's literally software can tell it how it should, what format it should be in, and then it can take that that shape, or that it can arrange itself in that way. So I showed you. Actually, go back here. Sorry. Let me get a more complicated adder. And anybody who works with or plays Minecraft and has worked with how their redstone system is, um, actually very similar. And this is it actually has they have the logic gates in the uh, in the redstone um, system in Minecraft, so that you can do incredible complex things, and you can go out there and find the people that have built a computer inside um, inside Minecraft using the redstone system and the logic gates that are inherently able to allow for certain things to happen. It's kind of interesting. Um, I was trying to find binary. Now this is not going to have. I'm not gonna I'm gonna find a picture here that doesn't have any labels or anything like that, because I don't want to go into details on how individual systems work. Um, I just want to kind of show an example. So this is an input and output system that can, in this case, it turns BCD into a decimal output. And I don't want to I don't want to try to explain too much of that stuff right now. But basically, you can see that it takes those same logic systems, and these are just our electronic um, symbols for those different logic gates, and through that it can do a function of, in this case it's a conversion function from one type of a binary type of input to a decimal input, um, and so these are the kinds of things that whenever if you put enough of these together, you can just keep building and keep building and keep building, and you're at the point that you can do millions of these things a second, of these logic functions. Um, so, oh, and I want to give a little bit of heads up. I am not an electronic engineer or um, a real deep. I'm not building microchips. I don't program them. I never actually developed an FPGA system. I'm just trying to explain from my background, which I do have some electrical engineering schooling that I took whenever I was in the Air Force, and now my work currently is as a programmer, a software developer, um, and so I'm just trying to give a little bit of I've touched on a number of these fields between these two, also. So I'm just trying to give you again a layman's explanation of how some of these things work. All right. So whenever we, you know what, I'm gonna leave that on for now. I don't actually know where this was from. It was literally just a picture I just pulled up, just for the purpose of showing a more complex series of gates. Um, but so whenever you put these together, and you can do millions of these logic functions per second, you can do incredible things with it. You can make whenever are what we consider kind of now um, uh, object-oriented programming, which is we're pretty close to. I don't want to say just normal free, speech pattern programming, but we are in a situation where you can, whenever you're writing code, most of it's done in text versus having to build logic in binary or in basic, which was, uh, again, I don't want to get too far into the weeds on any of this stuff. But whenever you can tell a computer with words to do a thing, and then it compiles that down into a mathematical function, which is then sent through these logic operators to produce numerical output or digital output, and then that is reinterpreted to things like graphical visuals and things like that. So it's amazing what we can do. But going back to an FPGA, so it's a field programmable gate array. What it is able to do is it's able to change up these systems, and with a live operating system running on top of it. Specifically, I'm going to reference a few things whenever I talk about this stuff with the Mister itself, because it is the FPGA device that I know the most about firsthand. It uses an ARM processor with Linux running on it to, while the machine is running, it can change the field program, the FPGA, into whatever format the core it's telling it to do. And the way that it knows what to flash it into are basically these openly available cores that people have programmed. They program these cores using what is called visual hardware language. Or wait, oh shoot, sorry, I'm just totally blanking. Hardware description language. Sorry, HDL. So they use HDL, which tells, it's a mixture between programming CAD, like computer aided, like drafting or designing a system physically, because they have to lay out how all of these gates are going to be arranged, and the logic that needs to be arranged on the chip. And whenever you merge, there's a number of programs that are built for the purpose of designing, basically of describing how the hardware should be arranged to make these logic gates work in these FPGA systems. These and to give you a little bit of a history, just so you can understand, FPGAs were originally built primarily for testing microchip designs, so that a company that makes microchips, I'm not going to say, please don't take my word that Intel uses this, but they probably have design people that do. Whenever they're designing a new microchip or a new a new process on their chips, what they might do is get an FP agent that can hold all of the processes that their new chip needs to hold, and then they will program it in a HDL and flash it onto their chips. And then whenever they get it all right, they can take that HDL, send it off to their production facility so they use the FPGA to test it and to make sure that it works. Once it's all right, they send the HDL, which is the design that they use to flash that FPGA, off to their production facility, and the production facility can take that and build those microchips statically, so they don't need to be modified in the field, for a much lower cost, because the FPGAs themselves have a really high cost, and they're like in the tens of thousands or hundreds of thousands of dollars each, depending on the stats that you have generally. There are some reasons why We can get some of them cheaper for the purposes of like the Mister. The DE10 Nano board, which has the Cyclone 4 on it, is only about $200. Or actually, it's less than that. I think it's around $120 or $130 now. But the reason for that is because Microsoft subsidizes those boards for learning purposes, and I'm going to switch for learning purposes, um, so that people in college that are learning to program it in the different hardware description languages are capable of learning at a reasonable cost to themselves. So that is actually why the D10 nanoport is as inexpensive as it is. So all of this goes to say that microchips are generally built off of these logic gates. FPGAs are able to flash those logic chips during lifetime. Sorry. Are able to flash them and produce basically the microchip functionality that they're told to produce and change that as needed while they're still live, or while the ARM processor or whatever controller is sitting on top of it is live. So all of that again comes down to the purpose of this, which is why do they make retro gaming, or why are they breathing new life into retro gaming? So whenever we talk about FPGAs, some of the commercial companies you might have heard about are like Analog, which use FPGAs to reproduce console systems from retro gaming to make basically so that you can put in your classic gaming cartridges into these systems and play them just like you were on the original system. The reason that works is because what they have done, and what these people that have developed these cores for Mister have done, is that they've taken the original equipment that was in these systems. So let's say I got my NES here. So an NES is a number of microchips that work together to allow you to play the game. There's the main microprocessor that handles all the logic in the system. There's a sound microprocessor, and there are a number of other chips that control different functions of the gaming system. So I'm going to use the NES as an example. So the microcontroller is a chip with a bunch of gates on it, and then the music audio system is a few microchips that have a bunch of gates on each of them. Whenever you so what they do is they take all of the logic gates in these systems and they try to reproduce all of the gates that were in those original microchips, and they try to fit them all together into one big microchip. Then they build all of that using a HDL and design the FPGA HDL to fit all of the individual microchips that are in the original system. Whenever they've got that done, then they set up with that all of the pins that would be the inputs and the outputs of the original NES system, with some variations, and they'll make it so that it works with modern technologies and things like that. They set up that core as in HDL using a couple of different technologies. A lot of them are using Verilog, I think, but I don't want to go into details on that because I'm not that knowledgeable on that section of it. and they are able to flash them live, so that they can flash a Nintendo onto the FPGA whenever they want, or they can flash a Sega, a Nintendo, um, all of the main retro consoles, and they also are able to flash. They've reproduced entire arcade systems, so all of the microchips that are in an arcade system can be reproduced in there. And they put it all. They build it in a language that can flash the DHL. Or they write it in DHL so it can flash those gates onto the FPGA to reproduce the individual microchips that would have been in those systems. So what it does is it basically functionally makes that FPGA work exactly like those original systems do, as far as they can. Now, there are still limitations on that people have based upon what they can learn about the microchips, how they can figure out what the outputs are. A lot of it is trial and error and finding out, but a lot of work has also been done in the emulation space for that purpose of reverse engineering those chips to make them so that they are, if not the same exact gates and the same function or in the same pattern, they at least function to the same for the same purpose, and they work at least equivalently to the original systems. And so one of the really cool things about these systems is they're able to reproduce the original consoles, arcade cabinets, any kind of electronic really are possible, up to how many gates are able to fit within that FPGA system. Again, Analog uses the same kind of technology. What they have actually done is they focus their systems on reproducing a single console, and they have great personnel that are reproducing these things as functionally as possible, so that they exist as close and they reproduce as close as the original systems. And one of the cool things about these types of systems is if you hook them up to a monitor, you don't have to worry about software lag getting in the process at all, because all of the original processes, as long as they're done accurately, or replicated accurately, they will work. The parts that are run in parallel in the original system run in parallel with the system. You don't have to worry about the timing issues that sometimes some situations you can run into with emulation, where one logic signal has to follow another because they all have to go in series, and they're limited by how many logical operations they can make within a time period. And these systems, they work, when done properly, they should work virtually identical to the original systems, and that's what makes them really cool, and that's why I like them. But I'm kind of coming to an end of what to talk about at this point. I feel like I've done a decent job explaining at least what gates are, how they're implemented in FPGA systems, and why they make a difference. Or not, maybe not make a difference, but why they're utilized and why people are so excited about some of these analog or some of these FPGA systems that are being used. So I hope you guys enjoyed this. You learned something, and hopefully you guys will like and subscribe and enjoy my content in the future.